All right, we're learning about sample proportions. So with continuous variables, we had our population mean and our sample mean. So our sample mean there was x with a little bar over the top. With discrete, it's not really an average mean, but our population proportion we've been calling p, and our sample proportion we call p with a little hat on top. So it's a similar concept, but not exactly the same. And it turns out that if you sort of know what P is and you do a survey of people, so let's suppose P is here, when you survey people, you won't figure out exactly what the true proportion is, but you will get something around there. And it might turn out that P hat was there when you did the survey, or P hat was there when you did the survey. This is distributed normally, and these give you formulas for mean and standard deviation as well. Or it's distributed normally if n and p are big enough, and these are your rule of thumb. Okay. So suppose a group of 32 people are surveyed, 29 like mashed potatoes. Now I apologize, this is very unrealistic data. Of course, all 32 would like mashed potatoes because they're fantastic. But just go with me here. 29 out of 32 is the sample proportion, and we can get an approximate for that. 29 out of 32, 0.91. I'll go three significant figures, why not? 0.906. So about 91% of people in our survey liked mashed potatoes, understandably. Okay. Now, as I'm sure you can imagine, we only surveyed 32 people. This is not saying that 91% of people in the entire world like mashed potatoes. This is just our best guess based on the survey. If you're familiar with the last topic, you might anticipate confidence intervals coming up as well. Okay, question 2. 38% of people suffer from back pain, and you survey 30 people. So for our first one, we want to calculate the probability that more than 11 people will suffer from back pain. Okay, now there's sort of two ways to do this. What you could do is a binomial distribution. Now this would be, in both cases, I'm going to say let x be the number of people out of 11 who suffer from back pain. Okay, so you could say that x squiggle b is 11 and 38% of people, so 38, estimate the probability that more than 11 people will suffer from back pain. So, sorry, that should be 30, not 11, 30. So the way we do it with binomial distributions is probability that x is greater than or equal to 11, roughly equals, and then we want to do a binomial CDF. So we're going to go into stats there. Distribution binomial BCD, the lower would be 11, and the upper, I think you can do a whole bunch of 9s or 30. Doesn't really matter. 0.38, and we should be able to get an approximate there, 0.627. Okay. Or the normal distribution approximation. This normal one is sort of this video's thing. This was the previous video's thing. Okay, so the normal distribution, we got to use these formulas. So the mean is p and the standard deviation is that other horrible formula. So the mean is p and the standard deviation is root p1 take p over n, which I think was the right formula. Yes, it was. Okay, so why did I not give myself more room there? There we go. So the mean is p, which is 0.38. And with the standard deviation, this would be root of 0.38 times 1 take 0.38 all over how many people we surveyed, which is 30. And we can work out what that is. So .0886. Okay, now, therefore, and it's going to be a bit funky, p hat is distributed normally with a mean of 0.38 and a standard deviation of 0.0886. And we can sort of see what that's going to give us. So if we want more than 11 out of 30, what I'm actually going to be wanting is probability that when I do my survey, p hat will be bigger than 11 out of 30. Roughly equals, and we're going to use normal CDFs to figure this out. So let's see if we can do that. Stats, dist, norm, NCD. We thought we were done with normal CDFs. We were not. 11 out of 30, a whole bunch of 9s. Or technically, the highest it can go is a 1, but your calculator doesn't know this because it doesn't realize we're talking about probabilities. 0.38. If we do that, we're going to get 0.559. Okay. Okay, now that was our guess using normal distributions. And what I want you to notice is that they're pretty similar. Pretty close, I'd say. It's not a bad guess. Now, less than 5 people suffering from back pain. So again, if we did the binomial method, we'd be looking at, let's go stats, distribution, binomial BCD. The lower would be 0 and the upper would be 5. Less than 5, the upper should actually be 4. You've got to be really careful. So with binomials, if I'm looking for the probability that x is less than 5, therefore that's the probability that x is less than or equal to 4, because it doesn't include 5. So you got to be real careful there. Everything here should be fine. So we got basically nothing, 0.00294. I think I've got around that. Yeah, I do. 295. Okay. And with the normals, this is the same mean and standard deviation from before, but the probability that p hat would be less than, so it's less than 5 people who are suffering from back pain. I'm going to go with the less than or equal to 4. So less than or equal to 4 out of 30. Roughly equals. If you want to get really precise here, you can talk about like rounding numbers and stuff, and you can go like 4.5, but this is just like a really rough idea of what we're doing here. So normal, lower, upper would be 4 out of 30. And then the standard deviation here and mean, I think they're the same as what they were before, so that's fine. And we get a really small number, 0.00268. So it's basically the same. So pretty much what I want you to think of is that these are the actual answers, and these are our estimates using normal distributions. Was our method reasonable? I'm going to say yes. We can assume that p hat, which I'm going to struggle to draw there, p hat, is approximately normal. Right, now, normally you wouldn't have the info that our guesses were pretty good. So that's already some indication that it's approximately normal. But we want to use these rules of thumbs. So NP and N1 take P. So if we look at NP, so that's 30 times the probability of success. In our case, success is having back pain for some reason, 0.38. Let's have a look. So 30 times 0.38 is 11.4. And N1 take P is 30 times 1 take 0.38, which is 18.6. And really importantly, these are both greater than or equal to 5. So we assume that it's normal. Assume P hat is normal. And so that's why we can assume that it's approximately normal. It's using those two sort of rule of thumb things. Don't ask me why that's true. Stats is a very weird field. Okay. To test this result, I surveyed the math methods class and I find that only 2 people suffer from back pain. So given that the chance that it was like less than 5 people was incredibly low, I would say that having less than 2 people suffering from back pain is nearly impossible, because it's like a 38% chance that people do suffer from back pain, and I would expect more than 2 people to suffer from it. But nonetheless, I've surveyed my methods class and I've found out only 2 people suffer from back pain. How the heck is this possible given all the work we've done up here to show that the probability is crazy low? I encourage you to have a think about that and pause the video. Hopefully you did that. And the answer is we have a biased sample. The 38% suffering from back pain includes all ages of people. The methods class is generally teenagers who may not yet suffer from back pain. And I apologize if you're a teenager, you have all that to look forward to. It's quite wonderful. All right, so you just got to be careful of your sample, but in general, if you took a proper random sample of people and only 2 people suffered from back pain, based on our work, we'd assume that maybe something went wrong with your survey.